talking about tiering next. So I'll first talk about what tiering is, and then I'll talk about our implementation in Gluster. Tiering is a logical volume which is internally composed of different things. For example, fast subvolume. I got slides. Fast subvolume and a slow subvolume. You could have a subvolume which is secure or not secure. Thank you. I feel free now. You could have a subvolume that's is compliance-based, so maybe one subvolume has its hold time, so you can't delete those files, and another one has expired, which means you can delete them. That would be a compliance use case. Compressed or uncompressed would be another one. The list goes on and on. We're going to probably do a demo with AWS where we do expensive subvolumes. That would be one, and a non-expensive other would be the other subvolume. So two subvolumes, one expensive, one not expensive, right in the cloud. Hopefully we'll do that live on Gluster. So tiering is a timely feature. It's been around for a long time. I know EMC did this like in the 90s, but and IBM too. But why is it popular now all of a sudden? Why are Ceph and Isilon and other scale-out systems implementing tiering? What was the impetus for that? Well, I see two. One is there's diverse hardware that has come about in recent years. Obviously SSDs and persistent memory is coming. We have different types of disks, shingle drives, and so on and so forth. And so that's happened. And then another thing that's happened is software-defined storage has opened the door to new levels of customization in how you do your configuration. So with software-defined storage, you expect to be able to custom, and that really is exactly what Gluster's forte is. That's even going to be our motto, possibly. Storage your way. So tiering fits well as a play in software-defined storage, and it fits well with diverse hardware. So that's why we have it. Next slide. And specifically, when I talk about diverse types of storage, well, with scale-out systems, erasure codes has come about in the last few years. And erasure codes are wonderful because you save money. You don't need as many disks in order to get the redundancy that you would like. But they do come at a cost. And the cost is various types of costs. The coordination between the back-end disks for blocking, maybe extra transactions to do IOs, math to do encrypt and decrypt data that's coded. So we want to have erasure coding, but we don't like paying the price. And this is where tiering can come into it, and this is why Ceph did it, and that's why we're doing it so quickly. We're not putting this in slowly. We're really pushing it in as fast as we can, because we want it to be alongside erasure coding, and we want erasure coding to have a speed bump. But we can't get that speed bump in all cases. It really depends on the I/O patterns. We would like a cache which works in all cases. So you always are able to put your fast data that's used frequently into a fast tier. But the problem with this is the migration of data is quite expensive. And it's not like a memory cache because of the expense. In a memory cache, when you evict data, it's less expensive than it is when you evict data on a slow tier. You have twice as many I/O accesses potentially. And so what we have is instead what we call a slow-moving cache. A slow-moving cache means the set of hot data changes slowly over time. It cannot change quick the way it can in a memory cache. And I'll have to show some benchmarking slides shortly. And another difference between a memory cache is that the index is really large. I implemented a cache that was a memory cache. It was really a small cache, and all it was supposed to do was aggregate data for compression blocks. I was able to use a red-black tree for the index because it was so small. I cannot do that with, well, I could, but you'd have difficulties with the index because of the sheer size. If you have a disk which is terabytes large, and you have many small files, and you're talking about millions of files, which you potentially have to track their heat on them. And so the index gets to be really big, and so you have to solve that problem. So, next slide. All right, so I'll talk about the implementation and how we solve the indexing problem, at least in our first go. But first, I'll just spend a moment talking about optimizations. So the nice thing about tiering is, since everybody has sort of reached the same conclusion that this is a useful feature at the moment, there are lots of models to look at for ideas. So, for example, we can go to Ceph, we can go to DM cache, and there's one I heard about yesterday, which I hadn't heard before, called B-tier, which looks kind of interesting. Ben England, the performance guy for Gluster, has come up with a list, a compiled list from Ceph people. We met with them last week. Here's a list of the sorts of things that we can do. One is migrate off a hot tier large files rather than small files. In other words, try to utilize the hot tier for small files. We can try to distinguish sequential versus random I/O, because if it's sequential I/O, it may be more likely that the I/O or the data set is only going to be touched once rather than many times. And DM cache, I believe, does that. We can have access counters, so we don't promote something if it's only going to be touched once. We promote only if it's touched multiple times. We can use ODirect, so we don't pollute the Linux cache. When we do a promotion, we're not going to be using it. It doesn't need to go into the Linux cache. We would like to potentially utilize the sharding feature. The sharding features, if it was in the same graph, would mean that if you have a large file, but you're only touching one small piece of it, well, you don't need to migrate the entire large file into the hot tier. You only need to migrate the particular shard that you're interested in, and the rest can stay where it is. That would be really nice. And finally, a lesson we learned from DM cache last summer was that the hot tier is not necessarily utilized as well as we liked with DM cache. And what the criticism was that they had free space on the SSD, but they were not populating it with hot data for whatever reason. So the lesson is, use the SSD or the hot tier. If you have a hot tier, put data in it until it's full. When it becomes full, then you start to try to be intelligent about what data you event. Okay, next slide. Okay, so the next few slides are about our implementation in this first version of tiering. So I said a moment ago, we got an issue with indexing. The indexing is big. So two models to look at. One of them was DM cache, and one of them was Ceph. Ceph was more like us. DM cache is in the kernel. And also, DM cache is block-based. So I believe they use extents and a B-tree to index data. That really would work well for a file-based tiering system. We looked at Ceph and we looked at the Bloom filters. And at least originally, the Bloom filter problem was that they didn't implement counters. So for example, if you only touch a file once, that would trigger potentially a migration action. What we wanted were counters where you only trigger a migration on, say, the third access or the fourth access. And the Bloom filter didn't, at the time, we couldn't see a way to do that. I think that they have cracked that problem and they're going to get that feature. Now, maybe we'll go forward and check that out and maybe do it too. But what we said was, well, we'll do as a first run the SQLite database. Have a database store this information. Okay, so A database. Can you put a database in a storage system? Will it scale? Will it be fast enough? Those are really good questions, and I was a little skeptical about the idea. The thing with an SQL-like database is that it has a model. Swift uses it. They don't use it in the I/O path. They don't use it exactly the way we're thinking of using it, but they do. It does have a track record of being reliable, at least in that setting. And since we've worked alongside Swift people, it was, that gave us some level of comfort. Well, anyway, we developed an API which treats this problem as a black box. So we can swap out a different database, or we can swap out a Bloom filter, or even something that Becky talked about yesterday, having to do with timing wheels and cuckoo hashes. That's all possible because it's an API, and we do treat this as a black box. For now, what we'd like to do is try to get this database performance up. We currently want to avoid our IOs touching the database. So we can have a write-back cache to bunt the batch database transactions and then flush them out. Another thing we're looking at is sharding databases. This has been proposed as a way to contend with the scaling problem that you have in databases. If you have lots of small databases rather than one large one, that may lessen the problem of that you get when the database gets big. And then databases do defragmentation every now and then, and we can schedule those intelligently. I think that's called vacuum in the SQL world. So we're going to look at that, but also stay open. We will stay open for new solutions. We're not closing any doors. All right, next. Okay, we have a second part of implementation is capturing IOs, because when an IO comes in, we've got to store the time that it arrived, because this drives when we migrate or if we migrate. For example, we want to know if data should stay on the hot tier. So if we are having IOs which touch data on the hot tier, then we know it's hot. If we don't receive any IO for it, then we consider it a candidate to be demoted. Well, this change time recorder does that. What it does is it just captures IO times as they come in, and it has to distinguish internal versus external IOs, and it uses the PID for this. Soft by default, but is enabled when you start a tier volume. Okay, next. Okay, DHT had a lot of interesting changes. First was LS. The first time I got, so we have stacking of DHTs. We have a tiered DHT, a tiered translator, and then the subvolumes of that are DHT instances. So we have a DHT on top of a DHT. It's stacking. That broke LS. That broke the LS command. And it turned out the reason was well, as many of you know already, we maintain a cookie when the read-dir occurs and multiple passes of it go through to complete. We were not maintaining that properly, and one DHT was stepping on another. Well, so why don't we just have two cookies? One cookie for the tier and one cookie for the DHT. That was my first fix when I was just prototyping this last fall. It was a 64-bit cookie. I just took a little few of those bits and I said, this is going to be for the tier and this is going to be for the DHT, and we'll just start two cookies in there. But now we're polluting that cookie, and you only have 64 bits. It turns out if you start to use too much of it, well, you have less bits left over for the offset of the directory, which is where you left off in the last LS. So we start all these DHTs, and each one is taking a cookie. Well, we're going to run out of bits pretty quick, and that's not acceptable. So this was a tough problem, and it lasted a while. But what we landed on was just keeping a single cookie in there, which represents the client that you last talked to for that device. And that seems to have worked. We haven't had any bugs. We had a close call with a bug having to do with snap, and how snap and the original volume and the snap volume are in the same graph, and that seemed to cause some issues, but I don't think that is going to hurt us because we weren't able to recreate it. So it looks like this has worked. That's in the code. The hash subvolume DHT is hard-coded. We don't use the layout to dynamically determine where a file is. It's fixed on the hot volume. So you always go to the hot volume first for an I/O, and only on a miss you do a lookup all and go to the slow. That was another change. There's some strange issues where, DHT thinks he's the only DHT instance inside of a graph. And so he sometimes in the code expects the context to be populated and correctly set. Actually now there's 3 of them, and maybe one of them said it, but the other didn't. And they have some issues there with stale files and so on. So it's some really kind of difficult bugs there, and those have to be dealt with. Okay, so IOs during migration have to be dealt with, and IOs during graph switches. IOs during migration. When you have an IO during a migration, currently in Gluster, it won't succeed because it's locked, if I understand right. So we don't want the IO to just block. We want or stop, or break, not succeed. We can't return an IO error. I don't think we should even do that when we rebalance bricks, but let's anyway. I hope we can crack this problem by having a blocking block. When we go to touch that file, rather than just erroring out if somebody else is locking it, we'll have a lock and we'll wait for it to be freed with a timeout. There's no interface for that as far as I know in Gluster, so we'll have to create one. IOs during graph switches. Well, when you create a tiered volume, there's a brief window where this graph exists, but the subvolumes are not ready to be used yet. So you have this really peculiar window there that we had to deal with. DHT and the tiered translators have different X-header namespaces. You have to make sure they don't clash. Let's see. And we want to leverage all the enhancements that are coming for rebalance. They're making, DHT guys are making the rebalance a lot faster, and making it multi-threaded, etc. So we want to utilize that too. That will speed up promotion and motion. All right, with Gluster D. So, Gluster D was actually one of the hardest parts. It really was tough. Fortunately, there's a lot of operations or things inside of Gluster D that you can reuse. The good side of that is, well, you don't have to reinvent the wheel when you attach a tier dynamically. But the bad side is you get all these if statements everywhere. If this volume is tiered, do this. Or if that, or you just copy the whole thing, and I had a fix rejected when I did that. Don't copy the whole function. Put an if statement in there. Well, I mean, I think Gluster D is tough. I think modularizing it is a great move. So even statistics are a hard problem. You know, you think statistics would be simple. To get the statistics of all the number of files you've promoted or demoted. Well, actually, you got to go to every other node and you've got to bring it back and you've got to compile that into one number and then report that back to the CLI. So you just dance with nodes talking to each other, and that's quite complicated. Okay. All right, so benchmarking. Well, it turns out many benchmarks are poor fit for Turing. Why is that? Because people use memory caching, not volume type caching. And last year, when DM cache was being looked at by the performance team at Red Hat, they initially complained. They said, "Wow, this tiering doesn't work at all." And I think Ceph had a similar experience. The performance team, when they first looked at Ceph's implementation, said, "Well, hey, this thing's not really working that great." Well, it had to do with their benchmarks most likely. They were expecting cache-like, memory cache-like behavior. And what you really need is a stable I/O pattern where data remains on the hot tier for some period of time, preferably on the order of minutes or hours. So we have, and two examples of that, like let's say some videos. You have a video streamer and some videos are popular on the order of weeks, or one I got yesterday, which I think is pretty cool. Hospital, where patients come in, and these patients stay at the hospital for a few days, so their records are being looked at for a few days, and then they leave the hospital or they die, and then they you don't need to look at their records any longer. So.
I'm pretty sure they leave the hospital when they die too.
So, yeah. It can be a victim from the hospital. So we have actually the FIO is not a new benchmarking tool, but an option to it has been added to work better for stable workloads. And it can be utilized for all the different tiering families in the Red Hat org. I mentioned scalability problems, and I mentioned we have our door open and other solutions. Okay. This is actually time on the x-axis. And on the y-axis, we've got the set of files that are hot. The set of files are hot. What I mean by that is we create, say, 10,000 files, and every file name is a number, F1, F2, F3, F4, F5, F6. What files are hot? Well, we take a standard deviation, a Gaussian thing, and that's a number with a median, with some, 97% to the left and right, and we slowly move that, to the right, move that. And as we do that, we're just taking a median, and we're slowly moving that. And as we move it, well, it's a slow-moving cache. That's the set of files that are cold or hot. And you get a pattern that looks like this. Okay, so near-term next steps. That is like in the near future, not 4.0 time frame, but before that, would be read-only caching. There's it's a startup that does tiering. Name escapes me. They do read-only caching. And I think read-only caching is a good use case for us. So I'd like to try to implement that. Time-based migration. So I think the snapshot feature has a scheduling service. I think you can schedule when a snapshot occurs. I think we could. We might be able to leverage that. We might be able to use it for tiering 2 and say, okay, at 3 o'clock in the morning, migrate your files. We want to be able to support volume expansion, so we want to be able to add and remove bricks to a tiered volume. We don't do that currently, but it's just a technical issue that we have to solve. And scalability, we've got to work on that. Okay, further out. We might have the data classification feature, which is a lot more than cache tiering. Those are some of the things I put on the first slide. The syntax might be such that you attach volumes under the bricks to create tiered volumes. And you can create an arbitrarily number of DHTs to do arbitrarily complex, and this is really software-defined storage nirvana, where you absolutely have total control over everything that goes on your data. Combinations of security, SSDs, this, that. It's just a giant tree. You could even do rack-aware placement. Okay, so these disks are on one level. I'm not finished. But go ahead.
Just placeholder, it's all good. So that does sound like a very powerful thing. We're going to have to get some good admin tools, because that would be an administrator's nightmare, having to deal with all of these multiple options in 1,000 friggin' Gluster node with this layer on top of it. That's like a three-dimensional matrix of what needs to be done for a sysadmin. So
yeah, I agree, and it was very hard to come up with a solution, but I think with some brainstorming, we may be close. You keep the volume concept, and then you have an idea of a coalesced volume. So you can go backwards to any volume on that tree and look at it. But you see how we've got a volume here? We have to give it a name, slow pool, and then we reference it with this. But you can go back to this slow pool and collect statistics, or you can do it at the granularity of the whole thing. So I know it's not best, but it's the best thing that's right now.
Cool.
Yeah. So I don't think there's any more slides, no? So that's it for cheering, guys.
Cool. Why was it chosen to implement as DST over DST instead of having it on the node, where it is truly a cache and the file is never evicted out of the slow disk?
You mean on the server?
Yes.
Because we wanted to support multiple nodes in the same volume?
You could have one SSD on every node.
You could, but you'd have to hard code it. I don't think you'd have the same level of flexibility with that, though it could work. It could work.
Because he could have avoided the rebalance SSD.
Well, yeah, possibly. I don't know if it would have given the same flexibility to the user, but it could have been done that way. Yeah, server-side sharing might have been an idea. But you've got to tell that SSD has got to be on the same volume as
that would probably be a future enhancement.
That sounds like it would be a common deployment scenario.
So anyway, the CTR will know what to move. Yeah, it depends on how we express that as a policy. Based on that.
From an admin point of view, when you're provisioning a server, it's a very simple thing to go, let's have 20 disks in this particular thing and 2 SSDs just on every server. That's a simple thing. So,
One thing we wanted was the flexibility to attach and detach SSDs as needed. So you can take an SSD, walk over, put it on that server, and then take it off the next day and walk over and put it on a different one.
that's probably catering to something that probably wouldn't be used much. I mean, there would be use cases for it, but in the scale-out world, people don't want to walk into a data center and do that. I mean, there will be some home labs and stuff, or smaller providers, but the big ones they want like 3 types of machines, and those 3 types they're the configurations we've got, and that's it, So.
Well, I know the price of SSDs has gone down to the point where maybe it's not outrageous to consider that it might be the one on every server. Yeah.
It's just thinking out loud.
No, definitely. It's good feedback. Well, I think we'll go to the next.